There is one more thing that we can do by manipulating these exponential models without actually solving for either of the variables. And that is to determine the percent change. So we had these models that were described in terms of percent change. We can also describe an exponential model in another way, and then calculate how we would describe it in terms of percent change. So here's an example. 10,000 copies of a limited edition collectible card are initially sold. After 15 years, only 10 cards in good condition remain in circulation. Wear and tear on collectibles follows an exponential decay model, so that says we're actually going to want an exponential model here. And we want to know what percent of the cards are destroyed each year. Okay, so in this problem, we have a lot of steps. Our first step is to figure out the multiplier, because we weren't told that the multiplier here. But to go from 10,000 to 10, well, we're going to multiply by 10 divided by 10,000, which is 0.001, 1,000th. We multiply by that number after 15 years. We initially have 10,000 cards after 0 years, so that's the initial amount. So we can write the number of cards after t years as a function of t, n for number. N of t is the initial number, 10,000, times the multiplier, 0.001, to the power, well, t minus, the starting time was 0, so just t over 15, the time it took to multiply by that number. We want to know what percent are lost each year. We'll rewrite the exponential part of our expression, so just the part with the exponential, in this way. So we have t over 15, that's 1/15 times t. So we have 0.001 to the 1/15th times t, which is 0.001 to the 1/15th to the t, using the power of a power rule. So the multiplier each year, every time t goes up by 1, we multiply by 0.001 to the 1/15th, which is about, and I'm going to carry 3 decimal places here for reasons that are going to become clear in a moment. 0.001 to the power 1/15th is about 0.631, which is 63.1%. Right, just multiply that by 100. And that's why I rounded that to 3 decimal places, because I want to round a percent to 1 decimal place. So each year we multiply by 63.1%. What do we need to subtract from 100% to get 63.1%? Well, that's the same question as what is 100 minus 63.1? Right? And 100 minus 63.1 is 36.9. What do we need to subtract from 100% to get 63.1%? 36.9%. That tells us that 36.9% of the cards are destroyed each year. Okay, so this is our full reasoning for this problem, with every idea written out real clearly. Let's see how we would actually write the work for a problem like this. In this example, we're told that after an economic boom, the population of a small town doubles over the course of 5 years. And we want to know, by what percent did it increase each year? Well, okay, so it's doubling. So that means our multiplier is 2. Our population is going to be our starting population times 2 to the power. Well, it doubles over the course of 5 years. The time it takes to double is 5 years. So we're going to say t over 5. Okay, we weren't told the starting population, but that's okay, because what we're actually interested in is manipulating this exponential part. 2 to the t over 5 is 2 to the 1/5 times t is 2 to the 1/5 to the t, which means that what we multiply by every year, which we can call m if we'd like, is 2 to the 1/5, which is about, I want to give a percent to 1 decimal place, so I'm going to round this to 3 decimal places. 2 to the 1/5 is about 1.149. Okay, so this multiplier is bigger than 1. The population is going up. We're going to have a percent increase. So we have a percent increase. We want to know, what do we have to add to 1 to get that number? We're going to just subtract 1. 1.149 minus 1 is 0.149, which is 14.9%. The population increases by 14.9% each year. And that's all there is to it. We're just manipulating the exponential part to rewrite it so that the exponent ends up being 1. And then we're figuring out what percent change that's related to.